Okay, recording has started. So, welcome. This is the EECE 1202 Exam 2 review session. This exam is mostly about op amps. So, we're going to be talking about op amps. If at any point you have any questions, just raise your hand on Teams or here. I don't know if I'll get notified if you do it on Teams, but you can say something in the chat or turn on your microphone and we'll address anything. So, we're going to talk about op amps, kind of some basics. Some normal topologies that you might see, and then some unique topology questions. So you might get a question where it's not exactly an inverting amplifier, but it might be a little bit different. There's an extra resistor, and so we'll do a couple of examples on how to derive what the output voltage is for a given input voltage, because there might be questions like that on your exam. And then for filters, we'll talk a little bit about passive filters, so like the high pass, low pass, capacitor, resistor, or RC, RL filters. And then we'll talk about active filters, which are the ones that we're talking about using op amps, where we can have a gain that's bigger than 1. And then some examples of filter circuits and maybe some Bodie plot questions like on the homework. Because if I know Dr. Kogan, the exam's probably going to be a lot like the homeworks, and I've seen some of the homework questions, so we can build on these examples as we go. But to start off, op amps. So op amps, of course, are these little guys, the triangles. And the kind of these op amp circuits have 3 kind of golden rules. You have these input voltages, the V plus and the V minus. Those are always going to be equal for these circuits. We know that the current going into those inputs is going to be 0. We can call that I plus and I minus. That's going to be 0. And the open loop gain is nominally infinite. So that means that you're really not limited by the op amp in how much gain you can get. You're limited by the circuit. That's why op amps are really nice. And of course, none of these things are true in practice, but for these questions, when we're calculating the ideal gain for these topologies, these are kind of the 3 main rules that we use to derive the outputs of the circuit. So there's a couple of other inputs. There's usually like a VDD, VSS or something, some kind of positive and negative supply rail. You don't really see this in our schematics, but when you're fabricating the circuit and when you're building the circuit, this is basically going to say the maximum voltage and the minimum voltage that the op amp can output. So these things aren't magic. They can't just give you any voltage. You have to supply it a voltage, and it'll amplify a signal to somewhere between the maximum and the minimum voltages. So that's a way that you can kind of think of it. They don't just amplify a signal. You need to have that maximum and minimum voltage, and it'll amplify it within that range. So again, these are the 3 golden rules, and we'll get back to those. So gain, you'll see it as AV. That's kind of like gain and a voltage gain. So gain is kind of defined as your output voltage divided by your input voltage, and that's a ratio in volts per volt. And of course, we can convert that into decibels, and we use this equation for converting into decibels. So 20 times the log base 10 of this ratio, V out over Vn. So this is important. Sometimes you might be asked to give it in decibels, but you've got the ratio, so you just have to be able to convert the 2. And if we do it the other way, so if I said that the gain was 6 dB, well, we know that 6 equals 20 log base 10 of V out over V in, right? So then we can do divide by 20. We have 6 over 20 equals log base 10 of this ratio V out over V in. And then to get rid of the log, we can raise 10 to the power of both sides. So this gives us V out over V in equals 10 to the 6 over 20, and you type that into your calculator. But so we can use this formula to go back and forth between the 2. It's not just going from the ratio to decibels. You can use it the other way. You just have to make sure you know how to get rid of these logs. So the inside of an op amp, I don't think you'll see any questions about this, but it's just interesting to know about kind of amplifier circuits in general. So you'd want for your amplifier, or for any kind of circuit like this, you'd want a very large input resistance. So if you think about something like a voltmeter, when you connect your voltmeter, you don't want any current to be going into it. So that's kind of a high input resistance on a voltmeter. So an op amp is kind of similar. You want it to read the signal, but you don't want it to have a lot of current going in if this is a high voltage. So you want to have a high input resistance. And then the voltage across this input resistor feeds into this voltage controlled voltage source. This is kind of how we can model the op amp, where it's clamped by the positive and the minus rails. And this is the equation for the voltage source. It's the gain times the difference between these two voltages. And again, this is not super important probably for your exam to know these things, but this is just a way that we can model it because we know that in our assumptions, AV is infinite and V plus equals V minus. So this gain AV times V plus minus V minus is like infinity times 0. So this model doesn't really make sense when we talk about our assumptions or our golden rules, but that's okay because the golden rules give you the nominal kind of gain and the nominal output voltage for a circuit. But if you start modeling a real transistor, you'll know these parameters, and you'll be able to model it a little bit more correctly. So that's kind of just introduction to op amps. I know you guys covered this in class already, but any questions about op amps so far? We're going to get into gains. Yeah?
I have one question with the.
Yeah.
If you have a Vout that's negative.
That's a good question. So a lot of times when you see that, it'll be an absolute value. See, I should probably put that here. But in a lot of ways, like a lot of times when you're talking about amplifier circuits, you're not really concerned about the positive or the minus. You're kind of concerned more about the magnitude of the gain. So your ratio V out or Vn, this one's nice because it has something about the magnitude, which is if it's 0.5, then that's a half, or if it's 10, that means your output is getting multiplied by 10. But it also can have a sign on it, so it can be a plus or a minus, and that tells you whether it's inverting or not. But the gain in decibels can't really tell you if it's inverting. It can only tell you if it's bigger or smaller, right? So a negative gain in decibels, like -3 dB, it doesn't mean that it's inverting the signal. It just means that it's attenuating it by 3 decibels. So the output is 3 decibels lower than the input. So yeah, so I would say that don't worry too much about the sign of it. Of course, maybe for this class, there's going to be questions like, does this circuit invert it? Is it going to be a negative? But when you're worried about the decibels and the logs and everything, just take the absolute value. Good question. Oh yeah, and yeah, another thing to be confused about is, yeah, if this ratio is negative, that means it's inverting. If your log is negative, that's fine. It just means that it's attenuating and not increasing. So let's go to our first configuration, the inverting amplifier. I'm sure you've seen this one before. In fact, this actually was an interview question for me for my Texas Instruments interview. They showed me this picture and they said, "How would you explain the gain of this circuit?" So in front of them, I derived the gain of the circuit. So these things are important and they could be interview questions. We're getting to the level now where everyone knows Ohm's law. They're never going to ask you what's Ohm's law, or if they do, you better get right. But something like this, they could feasibly ask sophomore level electrical engineering students, and some of them might know it and some of them might not. So op amps are important, especially when you get into analog circuit design and stuff like that. So we can derive this gain. So of course, V out equals negative RF over RI times VI. So your input voltage, this is your input resistance, and this is your feedback resistor. So if we wanted to rederive this gain equation of RF over RI, then we could use our golden rules. So say we know that VI, I guess it doesn't really matter what we know, but VI, we know it, and V out, we're trying to solve it. So if we know VI and we find V out, then we can find this ratio of V out over V in. Okay, so let's call this node X and think about the current flowing into this point. So say that there's current flowing here, we'll call that IF, and current flowing here, that's I in. Okay, so if we were to do KCL or Kirchhoff's current law at this node, we'd have I in is flowing into it, IF is also flowing in. And then we have I minus flowing out. So we know from one of our golden rules that the current flowing into these terminals, the positive and negative terminals of the op amps, is 0. So we can say that these two currents, IN and IF, are going to add up to 0 because there's going to be no current flowing in here. So any current going here is going to have to continue on through the feedback resistor. Okay? So we know this one, and that's our current equation. And if we do something with the voltages, then we can derive the gain. So one of our other golden rules is that the voltage at the positive input, I'll change up the color here. The voltage at the positive input is the same as the voltage at the negative input. That's the V plus equals V minus. Okay? And you'll see different notation for these. You might see like VP equals VN or something like that. But we're just talking about the voltage of these two nodes. So let's call that VP, VN maybe. Okay? So those are going to be equal, but we know that VP is grounded here. So VP equals VN equals 0. And that's just from the golden rules. And finally, we named this node X, right? We can see that node X, this is the same electrical node as our negative input. So that has the same voltage as this Vn. So we can say that Vx equals Vn equals Vp equals 0. Okay? And now we're kind of ready to solve our output voltage. So let's write this KCL equation in terms of these voltages, right? Remember Ohm's law is V equals IR. Okay, so we'll start here. So if we wanted to get this current I in, that is this voltage VI minus Vx over the resistance Ri, right? The voltage drop divided by the resistance gives you the current. So we can say that we're just going to rewrite this equation using voltages. So Vi minus Vx over Ri. And then IF, we'll call that V out is on the positive side. Vx is on the negative side, all divided by RF, okay? So we can add that one. V out minus Vx over RF. And we said that these two currents added up equals 0. Okay? So we can do some simplifications. We know that Vx equals 0. So we can cross these out. Vx, Vx. So, okay, so we can say that this is Vi over Ri equals V plus V out RF equals 0. And let's subtract our V out to the other side. Vi equals Vi over Ri equals V out negative over RF. And then, of course, if we multiply both sides by RF and get it over to the other side, and get the negative over to the other side too, that simplifies to V out equals negative RF over Ri times Vi. Okay, and this is our gain equation that we solved for, or that we were given in the beginning. So this is one of the easier examples to derive again, but you can see that all you need to do is remember your golden rules. And basically each time you do this, regardless of what the circuit looks like, it's going to follow the same kind of steps. Identify what the voltages are of these nodes. And you might have to use the mirroring property between these two voltages to get one of them. And then do KCL at these nodes. And once you do that, you express those currents in terms of the voltages, and you'll usually get to where you want to go. So we'll do a more complicated example. But the one other thing about this amplifier, this is an inverting amplifier. The one other thing I wanted to say is it has linear gain. So the reason you might be wondering why in a lot of these circuits we use inverting amplifiers instead of non-inverting amplifiers. Because to me, non-inverting seems nicer than an inverting amplifier. But the reason that the inverting amplifier is nice, and okay, let's go to the non-inverting amplifier. So for the inverting, we had V out equals negative RF over RI VI. Okay, and this is the non-inverting. And let's say for the sake of argument that RF equals RS equals 1 ohm. Okay, so let's simplify these equations. We can say V out equals 1 plus 1 over 1 VI, and this one is V out equals 1 over 1 VI, which is 1 plus 1 over 1 is just 2 VI. Well, okay, we shouldn't say it that way. In fact, I think this is gonna cause more confusion. Let's leave them. Sorry about that. Let's leave them like this, and we'll work with the variables. So the reason the inverting equation is nice is, say that we doubled our input voltage, and we said V out 2 equals Ri 2 Vi. What happens is when we double our input voltage, that means that V out 2 equals 2 times our normal V out. If you double the input voltage, the output voltage doubles because there's no additive terms here. However, the non-inverting, if we double our input voltage, plus Rf over Rs times 2 Vi, right? This is going to be like the 2 is going to distribute out to these. So it's going to be kind of like 2 plus 2Rf over Rs. So we have this extra factor of 2 that makes it not as controllable by the resistors. So in the inverting equation, the only thing that is affected by the gain is the resistors. So if you have small resistor values, it's still only going to be the resistors that affect the gain. But for the non-inverting case, you have this extra term of 1, which makes the gain a little bit more complicated. You get a little bit less control with your resistors. Usually it's not going to make that big of a difference if you have a big gain, but it's this property that is why we're using the non-inverting amplifiers. And there's some other properties that we'll talk about later, but if that's confusing, I would say don't worry about it too much. But the inverting amplifiers have this nice property, and then there's also, if we get to the summing amplifiers, you'll see that they're or some of the other amplifiers, like the difference amplifier, is kind of just based on the inverting amplifier topology. Okay, so the non-inverting amplifier has this gain of 1 plus Rf over Rs times your input voltage. Did I copy the circuit down wrong? Yes, I did. Oh, no, I didn't. This is right. Right, this is the right circuit. Your input is now on the positive, and your negative input is kind of grounded. Okay, so you still have these two resistors, Rf and Rs. And we can go over we could derive the gain of this one, but I'll save that. We have a couple of derivation examples that are probably more interesting or more relevant to your exam. So make sure you can identify too which configuration it is. So if on the exam you're given a circuit that looks like this, you'll save yourself some time in the derivation if you can recognize immediately this is a non-inverting amplifier. So one of the things to watch out for is which one is the positive and the negative input. So on the exam, they may give you the flipped version of the circuit with the positive on top. So I remember getting tripped up by this a lot, where if our circuit looks like this, and then this is our Rs, and that's grounded, and then maybe it comes around to this side, and then your positive input has some kind of a source here. Okay, these are really the same circuit and they're flipped, and the more complicated the circuit gets, the harder it is to flip it in your mind. So watch out for which one of the inputs is on top or the bottom, because if we switched it like this, that would completely change the circuit. Okay, so let's put it back to normal. And we'll come back to this one if we want to derive it later, but we have some more interesting examples. So the inverting, the non-inverting, and then the summing amplifier. And I think you guys do a lab over this one. Okay, so you're intimately familiar with the summing and amplifier. We'll talk about it real quick. So you can see that it kind of degenerates down to the regular inverting amplifier configuration if we have just one input. So if we were to ignore all of these guys, or if we were to say that V2 to Vn is 0, then this would look just like a normal inverting amplifier, where this is your Rin, this is your Rf, and it has the same behavior. And it looks like that in the equation too. If all of the V2 to Vn are 0, then it's just negative Rf over R1 times V1. So this is a nice property too. The summing amplifier, the derivation is going to be the same as for the inverting amplifier, except for instead of, so for the inverting amplifier, we had this I in, which was V in over R in. If we were to apply that same principle here, we would have, this is V1, or I1, sorry, I1, this would be I2, to be IN. And to solve it, you would just do the same thing, where at this node, instead of having just IN and IF, you would have instead of just having those two currents, you would have I1 plus I2 plus all the way up to IN plus IF equals 0. Okay, so then when you express these in terms of voltages, I1 would just be V1 minus V negative over R1, V2 minus Vn over R2, and then plus V out minus Vn over Rf. Okay, so it's kind of the same derivation, just with all of the input voltages, and of course these would all be 0, and you'd arrive at your gain equation. Okay, so nothing you haven't seen before. I don't know, do you guys know if you get an equation sheet for this exam, or a formula sheet, or op-amp? Okay, so definitely make sure that you can remember the similarities between these two, because this one looks complicated, but it really is just an inverting amplifier with multiple inputs. So this input is just copied and pasted and connected at this node. So if you can recognize that, basically instead of remembering two different circuits, you just have to remember one. The non-inverting amplifier, remember where the input goes and how this this negative side gets grounded. And the difference amplifier, I think, is the last of the basic configurations that we'll talk about. This one's a little bit trickier, and we usually have this assumption that R1 and R2 have this ratio, and it's equal to the ratio of R3 and R4. So R1 and R2 are the two resistors that are on the negative side. R3 and R4 are on the positive side. So you need this relationship to hold. Basically, R1 and R3 are both the resistors that are kind of on the input. R2 and R4 are in the denominator, and they're the ones on the side. Okay, and the difference amplifier is nice. This one actually works kind of how you'd expect an op-amp with two inputs to work, is it amplifies the difference between these two inputs using this gain equation. R2 over R1, that's the negative side resistors, times the difference between the positive and the negative inputs. Okay, so again, the gain equation, the gain factor is RF over RS. It's kind of like the same as the inverting amplifier, R2 over R1. And one property about this one is that it rejects the common mode input. So for example, say that your V1 was a sine wave that looked like this, and it was biased at 6 volts with a peak-to-peak voltage of 3 volts. Okay. And if your V2 was some kind of other weird signal with a weird shape, but it was also biased at 3 volts, the component in both of these that's the same is this 3-volt DC component. So if we look at what V2 minus V1 is, when we do V2 minus V1, anything that's the same between these two is going to get canceled out. And anything that's different is going to get amplified. So that's what we call common mode rejection. And this is the type of kind of differential input amplifier that you'll study in other classes later on. But this common mode rejection is really important. So basically, anything that's the same, any frequency component or DC component that's the same between your two inputs, is going to go to 0, and it's only the differences between the two of them that are going to be amplified. So even if they were both the same sine wave, you get no output because the difference between them is 0. Okay. Yeah. Yeah, so when we have a sine wave, right? So say that this is time and this is your voltage. Okay. Bias is what we call kind of the middle part of the sine wave. Normal sine wave kind of looks like this, and that's biased at 0 volts. But if we were to think about a sine wave like sine of, okay, and this is just a frequency and a phase shift. So that's going to be some sine wave that looks, something like this, right? If we were to say 6 plus that sine wave, this would be biased up by 6 volts. So the shape of the curve would be exactly the same, but it would just be biased at 6 volts. Yeah, basically like a vertical shift to it. So that's what we call a bias. It's just kind of, it's still oscillating. It's still going up and down, and it's still got the same peak to peak amplitude, but it's biased at a different spot. So when we talk about, and again, this is something you'll talk about in other classes, but if you have a signal like this top sine wave, it has a DC component of 6 volts and an AC component of 1. Right? You can kind of break a signal down like that. The DC component is the average value, which will be this 6-volt bias, and the AC component is how much it's changing over time. And so this common mode rejection means that the DC components cancel out, and the difference between the AC components will be amplified. So I don't know if there's going to be any questions about this common mode rejection, but it's an important concept, and they might ask, you might get some kind of questions about your understanding of the difference amplifier. But again, remember, it's only the difference between these two signals. So if there's anything that's the same between the two signals, that'll get canceled out. Okay, so I think that I have a couple of examples. If we want to go back and derive the non-inverting and the difference amplifier, we can do that later. But there's a couple of questions here that are a little bit wackier and don't really match any of our existing configurations. So this is an example where we have a 5-volt peak-to-peak source, and it kind of looks like a non-inverting amplifier, except we have this output resistor here. But let's just ignore everything, and we'll use our circuit principles to find out these currents and the output current. So, and we can find the gain, which would be output voltage. Okay, so let's use a different color. So we want to find gain. So we can call this V out is going to be there. I1 is going through R1, I2 through I2, I3 through this output resistor, and I out coming out of the op amp. So to start with, let's try and find the voltages at these two nodes. We'll call them VP, VN. Okay, and we know from our golden rules that VP equals VN. And we can see that the bottom of this source is grounded. So we know that the voltage at this positive input is just going to be 5 volts. Okay? Because we have 0, we're increasing by 5 volts, and we get to this VP node. So that's why we have 5 volts here. This is 5 volts. And from our golden rules, we know that those two voltages are going to be equal. So this one is also 5 volts at this VN node. Okay, I'll maybe zoom in a little bit so that we can see. So we have 5 volts here. And that's going to be useful for determining these two currents. Because again, if you can express a current in terms of the voltages on either side of the resistor, that's a big step for solving circuits like this. So we have 5 volts at this node. What else do we know? Let's try and find I1. Okay. So I1 is flowing through this resistor R1, positive to negative like that. So on the positive side, we have ground. That's 0 volts. And we're dropping to Vn. We know that that's 5 volts over R1, which is 1400 ohms. And if we can get a calculator out, it might be helpful for this problem because we're going to have a lot of fractions to get these into decimals. So 5 over 1400 is going to be 3.57 milliamps. Yes.
So, know how to do 0 minus 5 or 5 minus 0 again?
That's a good question. And that really is the question that plagues a lot of circuit analysis. In this case, it's because they gave us the direction of I1. So current in a resistor is always going to drop from positive to negative. And we can see in this case, it's not actually like this. We know that, or this is going to be negative actually, sorry. Negative 3.57 milliamps, right? We know that ground is on the left side and we have a positive 5 voltage here. So current is not going to flow from left to right, but because I1 is defined from left to right, the value of I1 is negative because it's actually flowing from right to left. If they didn't give us the direction of I1 and they said find the current through R1, then we could have chosen the direction to be whatever we want. But yeah, it's when they give you these arrows that you have to do it. Like for example, for I2, it's going to be positive on this side and negative on this side. So we take the voltage here minus the voltage on the left. Okay, and let's do that one next. So I2, on the right-hand side of it is V out. On the left-hand side of it is our Vn, which is 5 volts. And that's over 4100 ohms. Well, we're going to have to come back to this one because we don't know what V out is. But what we do know is our second golden rule, which is that I minus equals I plus equals 0. There's no current going into these op amps at these positive and negative input terminals. So if we switch up the color one more time, just to be confusing, we can do KCL at the negative input. Okay, KCL at this node here. We're going to sum up all the currents going in and all the currents going out. Well, it's defined in the way that I1 is coming in. So we'll say that's I1. It's defined also that I2 is coming in into this node up here, plus I2. And the current that's exiting the node going into the op amp is 0. So we can call this IN, but that's 0. Basically, what we can say is I1 plus I2 equals 0. We know I1 is 3.57 milliamps. So this implies that we can actually write it out. Negative 3.57 milliamps plus I2 equals 0, which means that I2 is 3.57 milliamps positive. Okay, so now we've solved for I1 and I2. What we need now is V out, so we can get the gain, and I3. But one of those is going to help with the other. So, okay, we know the currents I1 and I2. And so R2, we know the current flowing through it, and we know the resistance value. So that means we can solve for the voltage across it. What I mean by that is this equation for I2. Now we know what I2 is, but we need to solve for V out. So we can say that this equals 3.57 milliamps. And if we were to solve for V out here, do times 4100 plus 5, and I get that V out is 19.64 volts. Yeah.
you also do the gain equals 1 plus RF over R1? Would that work? Because I got the same answer that way.
Yeah.
Would that work in any case for this one?
That'll work if this is a non-inverting circuit. Yeah. So this is one where basically what we can do is we can redraw this circuit. This is basically a non-inverting amplifier with a load resistor. But if you didn't recognize that, you can go through this derivation again. And yeah, you'll get the same answer. But in the next two examples, they aren't basic circuit configurations, so we can't use any shortcuts. But yeah, that's a good point. If you can notice right away that this is a non-inverting amplifier, then you can just skip right to the equations that you know, and you don't have to rederive them. But here we're just kind of doing it numerically, right? So this is the right answer. This is the answer that you got to, right? Okay, that's good to know. And then finally, if we want to find I3, for I3, we have, we can look at the current through R3, plus minus here. We can say that I3 equals V out minus ground, which is 0, over 8,800 ohms, which we know is 19.64 over 8,800. What about 8,800? And that gives us, looks like 2.23 milliamps. Okay. And then our gain, of course, would just be, our gain in volts per volt is V out over V in, is 19.64 over, our input was 5 volts, which is going to be a little bit less than 4, I think. 3.93 volts per volt. Okay, you don't always have to put the volts per volt, but this is the ratio version. So we want to get the gain in decibels. Again, the equation is 20 times the log base 10 of your gain in volts per volt. That'd be 3.93 times the log base 10 of 3.3. Oh, my calculator doesn't have logs on it. Does anyone have the answer there? 11.88, thank you. Decibels. Okay. Gotta get a better calculator app. But okay, so this is just a quick example of how we can rederive these things. Again, yeah, this is the non-inverting amplifier just with a load resistor on the end. And it doesn't affect the gain equations, but if we look at the next example, I think this is an okay one to do. Yeah, let's do this one. So this one is also asking us just to find V out, which again, if we compare that to our input voltage, then that'll give us our gain. So this is a tricky one because it doesn't look like any of our previous circuits. It kind of looks like the non-inverting input. We look at that one. Kind of looks like our input is on the positive, and we have an RS going to ground and a feedback resistor. See RS going to ground and a feedback resistor, but our input is not exactly at this node. So what can we do? Well, if you remember the concept of a voltage divider, if you remember a voltage divider, basically when you have an input voltage feeding into two resistors like this, it's grounded, and you're looking for the output between the two of them, the equation is that the V out equals, let's call this R1, R2. It's R2 over R1 plus R2 times V in. Okay, so this is the voltage division equation. And it doesn't quite look like it, but this bottom part here is a voltage divider. So we can kind of, you can imagine that this is your R1, this is your R2. If we were to stretch it out to look like this, we'd say we have 3 volt peak to peak. Then we go up, and this is our 4K resistor. This is our 8K resistor. And then we have ground connected at the bottom of both of them. Okay, and in the middle, right here at this node, this is our positive voltage input. So if we want to find VP, in this case, it's not grounded, it's not zero, but we can use voltage division. So VP is going to be the middle of these two resistors, which is if R2, this is our R2, this is our R1, and this is our Vn. The voltage division equation tells us that this is 8 kilo ohms over 4 kilo ohms plus 8 kilo ohms times 3 volts. Okay, and this is 8 over 12 times 3, which is 2. That'll give us 2 volts as our VP.
Yeah.
Yes.
Another question. So how do we know whether to choose the 4K ohm resistor or the 8K? Is it because it's between ground and VP? So if ground was on the top side of this voltage divider, we use the 4K ohm resistor?
If ground was on the top side, well, it really depends on where you're looking for the voltage, right? So in this circuit, you could split it up a couple of ways, and you could redraw it as, I'm trying to think of the best way. Basically, we're concerned about the voltage between the 4K and the 8K resistor. So even if you drew it like this, basically all of the voltage from this 3-volt source is going to fall across this resistor and then across this resistor. So between these two resistors, the entire 3 volts is going to drop. And because the middle spot is what we're concerned about, then the first resistor that it drops across is R1, and then the second one is R2. Like if the top was grounded instead of the bottom, that gets into kind of like a ground is arbitrary type thing, where there'd still be some voltage here. It'd be 0, but then we just wouldn't know this voltage here. So if we had that circuit, it would just be a strange way of writing, I think. You probably won't run into that. Yeah. But yeah, it's really just about proportional voltage dropping. But yeah, voltage division is also something that it wasn't me, but a friend, I think a friend of mine got asked about the voltage division equation on an interview. So that's important. Okay, so we need to find the output voltage. What we found here is the input voltage is 2 volts. Okay, 2 volts right here. And from one of our golden rules, we know that the voltage here at this minus input is also going to be 2 volts. So let's see if we can find the output voltage. So if we focus just on the top half of the circuit, now we know, oh wait, change the color again. Let me just redraw the top half of the circuit. So we have a 2K resistor, we have 2 volts, 5K resistor. Oh, this is 2 volts, okay? At this point, we can kind of ignore the op amp, except for the current property. So this is our V out, this is ground. Let's define a current here, I1, a current here, I2, and this is gonna look a lot like the other examples. A lot of these op amps are these basic circuit analysis things are just going to be defining currents and then finding the voltage drop. So let's find what I1 is. If we defined it like this, the current is flowing like that. So we have 2 volts on the positive side, that's this node, and ground on the negative side. So this is 2 minus 0 over 2 kilo ohms, which is 1 milliamp. And then if we look at KCL, this negative input voltage, we can call this Vn, right? We have, and we've defined it a little bit weird, but 1 is coming out. So if we just do the currents going in, I2 is going in. Let's call this I minus. I2 is coming in, I1 and I minus are coming out. You can see it's really arbitrary the way that we define these things, but it's all going to work out in the end as long as you stay consistent. So if we define our currents like this, we have I2 coming in, I1 going out, and I negative, remember, is always 0 for an op amp. So we say I2 equals I1. So that means I2 equals 1 milliamp. And then finally, if our output voltage, let's look at the equation for I2. I2 is defined this way. So positive, negative. That means I2 equals V out is on the positive side. And on the negative side is this node. All of this node is 2 volts over 5 kilo ohms. And we know that I2 is equal to 1 milliamp. So if we solve this out, we get V out minus 2 volts equals 5 volts. So V out should be 7 volts. Okay. So that's how we can analyze a slightly weird op amp circuit. And this one is important because we use the voltage division to get the voltage at this node. So sometimes that's going to come up. And I think my third example does something similar. Yeah, it kind of combines the last two. So we can come back to this one in a bit if we need to and go on to filters. But this is another similar thing where maybe it's a little bit clearer in this image. We can use voltage division, this 6-volt source, to find the voltage here, where this is our R1 and this is our R2. And then we just have another source. Okay, so let's come back to this one and make sure that we can finish up all of our discussion on filters. But this would maybe be one of, like, I don't think you'll see a question this difficult on your exam. But if you do, it's good to be prepared for those things. So any questions so far on these amplifier configurations? Amplifier questions. Okay, so we'll go on to filters. So, whoops. This one. Yeah. This one, it looks like it's non-inverting. The way that we found our output voltage, our input voltage was, what, 3 volts? And our output voltage was 7 volts, so it was non-inverting. It may be, there might be some times when we find that the output voltage is negative. And remember, it's inverting if the output is negative and the input is positive, or vice versa. But yeah, this one we found to be non-inverting. And if you kind of look at it, it does look similar to a non-inverting amplifier. It's just that this input voltage is not so simply the input voltage, it's voltage division across this. So yeah, let's go on to filters. So you talked about these before, these passive filters. There's high pass and low pass. So this is an example of a low pass filter, a low pass RC filter. We're measuring the voltage across the capacitor. So does everyone remember how to tell if a filter is a high pass or a low pass? So say that I gave you where this is an inductor and this is a resistor, and we're measuring our output voltage here. Can anyone tell me if this is a high pass or a low pass? Wait, have you studied these before? Okay. Yeah, so this is a low pass filter because at high frequencies, the inductor acts as an open circuit. So at high frequencies, all the voltage is going to drop around here, and none of the voltage is going to be at the output. So at high frequencies, it has a very low output voltage. At low frequencies, the inductor acts as a short circuit, so all of the voltage is going to be on the output, right? So this is a low pass filter. And if you swap these two, and if you were to measure the output voltage across this thing, then it would become a high pass filter. But usually you're measuring voltage across the resistor, but you can do either way. Yeah, so passive filters, the maximum gain you can have on a passive filter is 1, and that's no attenuation. If there's any attenuation at all, then the output signal is going to be smaller than the input signal. That's because these are passive filters. There's no power being put into the signal. So the best you can do is attenuate it. The best you can do is decrease the amplitude of the output signal. So the cutoff frequency, again, is important. Every filter is going to have a cutoff frequency. So if we look at the Bode plot for a low-pass filter, well, that was awful. For a low-pass filter, remember the low frequencies are going to pass through, and at some point it's going to start to dip down. This is our frequency, and this is our gain. So at some point here, we have our cutoff frequency. And can anyone tell me the gain at the cutoff frequency in decibels or in volts per volt or anything? What's special about the cutoff frequency? Yeah, exactly. So if the gain here was 1, then the gain here would be 1 over the square root of 2, which is about 71%. And the reason this is called the reason this is important is because this is the half power point. So if we look at the power of the signals, 1 over square root of 2, when you're doing power, that gets squared, so it becomes 1 over 2. And that's why it's called the half power point. When we're squaring the signals, the 1 over square root of 2 becomes a 1/2, and the power of the signals is half at the cutoff frequency. So we basically say anything to the right of that is attenuated. Anything to the left is passed. Okay, so the cutoff frequency is important, and every filter is going to have a cutoff frequency, and that's one of the major points on the Bode plot that you can really be concerned about. There's a million points, but one of them is very important. And for a bandpass, it's 2 of them. So for passive filters, for RL and RC filters, you can generalize that the cutoff frequency is this. So you might have talked in your physics classes about RC circuits or time constants, charging and discharging capacitors, and they follow an exponential behavior. In those circuits, there's this parameter called tau, and tau is different for an RL and an RC circuit. So if you remember those, then you can remember this, and you can get the cutoff frequency. But I think for this exam, we're going to be more focused on active filters. So I don't think you really need to know all these passive filter things. There's going to be a certain number of op-amp configurations that we'll talk about, and those we'll talk about the cutoff frequency for each of those. But this is just, for your information, RL and RC circuits cutoff frequencies. So Bode plots. Bode plots are the gain versus frequency plots. Yeah, I already talked about this a little bit, but there's a couple of important things about the Bode plot. First of all, the x-axis could be either omega, which is the angular frequency, or it could be f, which is just the frequency. And I don't like the way my handwriting looks with the thin pen. And these are related with this equation, omega equals 2 pi times f. And that's important. I could definitely see one of your questions being you're given a sinusoidal signal, and in the sinusoidal signal, you can grab the omega parameter. And if they ask for the frequency or the period, you're going to have to convert it using this. So this is the frequency. F is in hertz, which is 1 over seconds. So we want to get the period of a signal, period t, as 1 over the frequency, and t is in seconds. So these are all some basic things about signals and frequencies and everything. About Bode plots, one really important fact is the slope of this part. The slope of this part is about 20 decibels per decade. And they probably throw that around a lot, but what that means is that when your frequency increases by a factor of 10, your gain will decrease by 20 decibels. And if you're in this linear regime, that holds. Once you get past the cutoff frequency, then we say that the gain is just the passband gain. But once you get, if you're in the linear regime, so this is a low pass filter, once you're above the cutoff frequency, then this 20 decibels per decade rule generally holds. So the gain decreases by 20 decibels every time you multiply your frequency by 10. And that's a consequence of these Bodie plots. So this is a low pass filter. Down here we have a high pass filter. So again, the same 20 decibels per decade would hold. We just have to be careful on which, if your signs are positive or negative, you're adding or subtracting your 20 decibels in the right way. So here, if I gave you the frequency, or the gain at this frequency, cutoff frequency divided by 10, that'd be about 20 decibels less than your passband frequency. Okay, so don't forget this 20 dB per decade rule. And remember, a decade is 10 years, so that's a factor of 10. That's the way you can remember it. Yeah, this is a low pass filter. So high frequency signals are passed without attenuation, and low frequency signals are attenuated. And then the last type is a band pass. So the band pass has two cutoff frequencies, the low cutoff frequency and the high cutoff frequency. And one thing that you should not get confused about is if you look at the left-hand side of a bandpass filter that has the low cutoff frequency, this is the high pass side. Because it kind of looks like a high pass filter. The high frequency signals are being passed through, and the low frequency signals are being attenuated. If you look at the right-hand side with the higher cutoff frequency, that is the low pass filter side. So it's really easy to get mixed up on whether if it's high or a low pass, it's going to have a low or a high cutoff frequency. But if you sketch it out, if you take a second to think about it, this one looks like a low pass filter because the lower frequency signals are being passed and the high frequency signals are being attenuated. So don't get mixed up on that either. Yeah, so these are the three types of filters I think that you're going to talk about. Did they talk about like integrating filters at all? Okay. Okay, yeah. Yeah, we won't worry about that then. So active filters in general are using an op amp. And because we're using an op amp, which can amplify, we can get gains that are bigger than 1 in these filter circuits. So before, when we had passive filters, your signal was either coming through at about 99 to 100% or is being attenuated. But here we can have a signal being passed through at a gain of 15, and then it gets cut off to about 0. So these are more powerful filter circuits than the passive filters. But the low pass filter looks like this. I wish I had a good way to remember that the low pass filter has the capacitor in the feedback loop, and the high pass filter has the capacitor on the input. There's ways that you can think about it, but if you have to memorize these, then maybe just try and memorize them. It's only 2 or 3 circuits you need to memorize. But the low pass filter looks like this. We have a feedback capacitor. Otherwise, it's basically just the inverting amplifier configuration. If we look back at the inverting amplifier, got our input and our feedback resistor, and the negative input is on top. Input, feedback resistor, negative input is on top. The only difference is this feedback capacitor turns this resistance into a complex impedance. Call that ZF, or the impedance, the feedback impedance. And that is just your RF in parallel with the impedance presented by that capacitor. So a cutoff frequency is 1 over 2 pi times RFCF. And this is a low pass filter. So remember, our Bodie plot is going to look something like this. Our cutoff frequency would be here. The gain in your passband, in the passband, we can pretty much ignore the capacitor. So if we ignore the capacitor, if we just pretend it's not there, then this is an inverting amplifier. So your passband gain is approximately RF over RI. And for a low pass filter, the lower your frequency, the more accurate that's going to be. Outside of the passband, or in general, you can use this equation, ZF over RI. So that's your feedback impedance at the given frequency. divided by your input resistance. And again, if you want to get V out, that would be AV times V in, which is VF RI times V in. Okay. So again, these types of questions, if you see this on your exam, it might give you an input signal that has a frequency, ask you for the output, and so you'll have to find what this gain is at that frequency. So for example, say that we're given a signal. Let's say, for example, that the cutoff frequency is 377 radians per second. That's our cutoff frequency. And this is a low pass filter. If we were operating at 37.7 radians per second, what is the gain? So we've moved by a factor of 10, right? And let's say that the gain in the passband gain is 6 decibels. Okay? If the gain in our passband is 6 decibels, and our cutoff frequency is 377, and it's a low pass filter, what would be the approximate gain of the circuit at 37.7 radians per second? Does anybody know? 3.
Frequency is passband minus 3 dB.
Oh, yeah, sorry. This is the passband gain. But yeah, so this is kind of a trick question, right? Because if our cutoff frequency, let's call this omega c, is 377, then we're operating over here. We're a factor of 10 less than that. So it'll just be your passband gain. And usually that's given to you. So 6 decibels. Okay? That's a tricky question because usually you're expecting to have to do some math. But yeah, don't get caught up on the easy questions. If it's a low pass filter and you're lower than your cutoff frequency, the approximate gain is your passband gain. And usually the passband gain is what's given to you, or you can solve for it using this formula. Okay, and we'll come up with some examples later. I don't have any, I have some examples. I don't think I have any examples for this one. Oh, I do. Okay, we'll do that one in a second. But yeah, we'll get to some examples like that because this is a really important question, and there's definitely going to be stuff like this on your exam. By moving factors of 10. So if we were to go to 3770 radians per second, what would be the gain? Well, then we're operating over here. Our passband gain is 6 decibels. So here's where we would have to use that linear property, where the slope here is 20 decibels per decade. And then you have to think about, do I add or subtract? So so one important thing about this linear approximation, this 20 decibels per decade, is that the shape of, I'm going to zoom away from this for a second for an illustration. This is a linear approximation. So if we were to kind of zoom in on this kind of elbow, this corner of your gain equation. Okay. This linear approximation looks like this. So it's kind of got a sharper corner than the actual cutoff frequency. So when we say our cutoff frequency is the -3 dB point, this linear extrapolation is not really at the cutoff frequency. That's where it starts. But if we were to continue this line, it reaches up to our passband gain. Okay, this is kind of important. So say that we are at our cutoff frequency. And let's say that that is 1 kilohertz. And our gain here let's just say that this is a 0 dB filter. Okay, 0 dB means no gain, no. If we were to look at the log formula, this would be 20 times the log base 10 of 1. Our gain ratio would be 1. The log of 1 is 0. So that's how we would get 0 dB, is when your ratio is 1. So this is kind of like a unity filter. If our passband gain is 0, then our cutoff gain is -3. If we were to look at a frequency at 10 kilohertz, then we can use our 20 dB per decade rule. Whoops. And the gain here at 10 would be 20 less than our passband gain or our cutoff frequency. Now that's the question you have to answer. Yeah, exactly. It is kind of funky. It is kind of funky. It feels like, since it's a factor of 10 away from your cutoff frequency, it should be using this -3 dB gain. But because this approximation meets up with our passband at this point, we have to actually say that this is 0 dB minus 20 dB, which is -20 dB. Okay, and that seems counterintuitive, but because it's an approximation, the further away you go, the less that difference is going to matter. So if you're a factor of 10 away from your cutoff frequency, you subtract 20 decibels from your passband gain. And your cutoff frequency gain is always going to be 3 decibels less than your passband gain. And it's usually nice to use decibels in this way because it's kind of linear. When we're working with factors of 10 in frequency, which is very common, it's nice to be able to add and subtract like this. So that was a point that I wanted to get through. I think we were working on that homework the other day. I think some students had come in, and yeah, this is something that always confused me when I was taking this class. So I made sure to figure out a good explanation. I hope that's okay. But if you're a factor of 10 away from the cutoff frequency, you use your passband gain when you're adding and subtracting. So that's the low pass filter. A lot of this is going to be the same for the high pass filter. The high pass filter looks like this. Instead of having the capacitor in parallel up here, we have it at the input. So remember the high pass filter, the Bode plot looks like this. High frequency signals pass through and low frequency signals are attenuated. If it helps to remember which one is which, you can think of, in low frequency situations and DC situations, the capacitor is like an open circuit, right? So if a low frequency input signal were to try to come in, it would be met with this capacitor and get blocked. That is why this is a high pass filter. Low frequency signals get blocked and get attenuated. High frequency signals will pass through this capacitor and get to be amplified by the op amp. So that's one way that you could remember that the high pass filter, the one that blocks the low frequency or the DC signals, has the capacitor on the input. But regardless, the cutoff frequency, it's kind of the same. For the low pass filter, it was the feedback capacitance and the feedback resistor that make the cutoff, because the filtering is happening up here. So we're using these two components. Here, the high pass filter is the filtering is happening on the input. So our cutoff frequency is 1 over 2 pi times the input resistance times the input capacitance. Your gain in your passband is again approximated. This is an approximation, because in the passband, we're assuming that the capacitor is having no impact, which is to say that when we're in the passband, the frequencies are high enough that the capacitor is acting like a short circuit. And so this becomes basically just an inverting amplifier again. Okay, so in the passband, we can approximate our gain to be this. And outside the passband, of course, we use the input impedance instead of the input resistance, where your input impedance is Ri plus the impedance of your capacitor at that frequency.
So would that gain outside your passband just to be like a random gain if that's not the passband, or what number would it give you?
Yeah, so outside of your passband, we're talking about this region here.
Yeah.
it should give you. So whenever we bring complex numbers into the mix, right? When we do RF over RI, that's going to be a number. That's going to be like 0.8. When we get here, it's going to be a complex number. So we can either represent it in rectangular form. It'll be something like 0.5 plus J3 or something, or it's going to have a magnitude and an angle. And the magnitude and angle is the more important one when we're talking about signals. So, and this comes back to the question earlier about, do we take the absolute value of the gain? A lot of times we're concerned about the magnitude of the gain. So if we look at the magnitude of this gain, and we look at the magnitude of this impedance, Zi is always going to be the impedance from your capacitor plus the impedance from your resistor, which is the impedance from your capacitor is 1 over J omega C, and the impedance from your resistor is just R. So when we're at high frequencies and we're ignoring the capacitor, high frequencies means this term goes to 0. And so your impedance is just going to be your R. As the capacitor becomes more and more important, as the frequencies get lower and lower, this term is going to start having an actual value. So the magnitude of your input impedance, basically the sum of these two numbers, is going to grow. So this Zi is going to start increasing as we get to lower frequencies. And so that's where outside of your passband, instead of having a constant ratio, this is going to start to depend on your frequency. As the frequency gets lower, Zi is going to get bigger because of that capacitor. And so this ratio is going to get smaller. And that's why our gain is going down. This is our gain. Right? So there's a million ways that you can think about this, but that's really what's happening mathematically. That's why these curves have these shapes. Okay? But yeah, the maximum value of this is going to be your passband gain. And that's going to be when your capacitor the frequency is high enough that your capacitor is not having much of an effect. Okay, but this is the high pass filter. Oh, and I put down here, does the order matter? The order does not matter of whether this capacitor is first or the resistor is first. Same thing up here. It doesn't matter if it's written the resistor on top or the capacitor on top, so don't get confused by that. Finally, the band pass filter combines these two. We've got a lot written here. But it seems like it should be more complicated, but it really is as simple as combining the low pass and the high pass filter, and you observe both behaviors. So if we have low pass or high pass filter, low pass filter, we'll kind of add them up, and we get something like band pass, where this is your pass band, and then these are both your attenuation regions. So you'll have two cutoff frequencies. Okay, and here again is what I've talked about. So the low cutoff frequency, this one here, which corresponds to that of your high pass filter. Kind of confusing, but you can use different naming conventions. It's the same as the equation for the high pass filter up here. You use your input resistor and capacitor to get your low cutoff frequency. For your high cutoff frequency, you use the feedback capacitor and resistor. Remember, the high cutoff frequency corresponds with the low pass filter. Your passband gain, again, in the passband, that's where we're assuming that the capacitors are not having an effect. So we can ignore them and just use the resistors in this inverting amplifier. And outside the passband, we do consider, again, this is an approximation. Outside of the passband, we do consider those capacitors. So we have to use the impedances, where ZF is this parallel impedance, and Zi is your series impedance here. So mathematically, they're really just a combination of the other two filter circuits. But if you can understand those other two filters, you just combine it for here, and then make sure that you remember that there are two cutoff frequencies here. But these should both have the 20 decibels per decade property. But just make sure that if you're doing a problem like this, your high and your low cutoff frequencies are going to be different. And so if you go in an order of magnitude away from one of them, make sure you know which direction you're going. Are you starting at this one and going that way, or starting at this one and going that way? And if you end up in your passband, then you can just use your passband gain, which is often given, or easily calculated. So let's move on to some examples with the filters. Any questions on these three circuits so far? So this is an example. First of all, this is a high pass or a low pass filter? It is a high pass filter. High pass filter, yeah. Because the capacitor is on the input, right? So this capacitor is going to block low frequency signals. So it wants us to find the output voltage. And let's make this a little bit more complicated. Instead of just saying 8 volts peak to peak, well, okay, we can, because I've already given this here, if we were to get a sinusoid, we could say that our input voltage, V in, equals 8 times the sine of 1000 t, V in of t, right? Or cosine, I guess. We haven't been given a phase shift, but it doesn't really matter. So you might be given a signal that looks like this, and so you'd have to recognize that this 1000 is your omega, and this is your amplitude. That would have been maybe a better example to give. But let's try and find our output voltage or our output signal as a response to this filter circuit. So first of all, let's find the cutoff frequency. So we identified that this is a high pass filter. This is a high pass filter. So our cutoff frequency is going to be 1 over 2 pi times Ri Ci, which is 1 over 2 pi. Ri is 1 kilo ohm, and Ci is 4 microfarads. 4 micro is 10 to what power? -6. So we get our cutoff frequency. This will tell us whether we're operating inside or outside of the passband. Two pi. Okay, I got the cutoff frequency was that. Yeah, I got that the cutoff frequency was that. Okay, and that's in hertz. This is the frequency in hertz, which maybe is not super useful. So we've got the cutoff frequency in hertz, and we're given that we're operating at 1000 radians per second. What we should really do is get the cutoff frequency in radians per second. So remember the formula there is omega equals 2 pi times f. We'd say omega c equals 2 pi times fc. So our cutoff frequency in radians per second is going to be 2 pi times 39.79. Or if you knew that you wanted to do this from the beginning, you could just say that omega c and ignore this factor of 2 pi. I could write that a little bit neater. Because we were going to multiply 2 pi on this side to get omega, multiply 2 pi on this side, and the 2 pi's would cancel out. So, but this is just getting us to do more steps and more math. Times 2 times pi. I get that omega c is 250 radians per second. Okay, if our cutoff frequency is 250 radians per second, and we are operating at 1000 radians per second, are we inside the passband or are we outside of the passband? Inside the passband. And the reason we're inside the passband is because this is a high pass filter. So the Bodhi plot looks something like this. High frequency signals pass through. The cutoff is 250. And we are somewhere over here at 1000. So if we want to find the gain of this circuit, we can use the approximation. The passband is negative RF over RI, which in our circuit, RF is 7 kilo ohms and RI is 1 kilo ohm. That's negative 7 kilo ohms for 1 kilo ohm, which is negative 7. Finally, if we want to find, or this is our gain on our passband. V out would then be V in times our gain in the passband, because we're operating in the passband. And our input voltage is 8 volts peak to peak. So 8 volts times negative 7 means that our output voltage should be negative 56 volts. Okay. So that's one example where we are operating in the passband. And as we don't have a ton of time left, if you were to find the impedance of this capacitor at this frequency, you would find that, so instead of using this approximation of negative RF over RI, if you were instead to do your voltage, your voltage gain is negative RF over VI. Let me do this down here. 4 microfarads. So AV equals negative RF over ZI, where your RF equals 7 kilo ohms, RI equals 1 kilo ohm, and CI is 4 microfarads. You would find that your ZI would be very, very close to, in magnitude, to 1 kilo ohm. Okay. I won't go through the steps there, but if you did the 1 over J omega C, your omega, right, is going to be 1000. So this is going to have a less of an impact than the resistor. So let's go to the next one. This is the other type of filter. This is a low pass filter, right? So let's find our cutoff frequency. Our cutoff frequency is going to be 1 over 2 pi times RF CF, which is 1 over 2 pi kilo ohms. And nano is how many? 10 to what power? Negative 9, yeah. Okay, and if we solve this one out, 1 over pi, 20 kilo ohms and 300, it's 10 to the negative 9. I get that our frequency is 26.53 hertz. Is that right? That seems right. I don't trust these numbers anymore. I did this a while ago. Okay, so then our omega C is 2 pi times our cutoff frequency, which is going to be 2 pi times that, which again is a little, if you knew that you wanted your omega before, you could just omit this 2 pi. That's 166.67 radians per second. Okay, and we don't have a frequency given, but if this is a, what is this one, a low pass filter? Low pass filter looks something like that. And our cutoff frequency is 167 radians per second. So anything less than that, we could approximate it and say that it is our passband gain. Anything bigger than that, if we wanted to approximate it, if it was an order of magnitude bigger, like 1670, it would be our passband gain in decibels minus 20. So real quick, let's do that. Let's do that approximation. So if we were to estimate our passband gain, that is negative RF over RI, which is 20K over 700. And 20,000 over 700, 28.6 volts per volt. We wanted to get that in decibels. We do 20 times the log base 10 of 28.6. And someone who has a better calculator than me can tell me that that is what number? 29.1? 29.12. Okay, so this is our gain. That's in decibels. .12 decibels. So now if we were given something like 1670 radians per second, we would say that that is 20 dB per decade. So at 1670, we would say that the gain is approximately 29.12 minus 20, which is 9.12 decibels. And if we were to go one order of magnitude to the left, 16.7 radians per second, we would not add 20 decibels. If we went one order of magnitude to the left, we would be solidly within our passband. And so we'd say that the gain is 29.12 decibels. And if we're at our passband, at your passband, remember that's our minus 3 dB point. So it would be 29.12 decibels minus 3 decibels, approximately 26.12 decibels. Okay, so that's how we can go in order of magnitude either way. If you wanted to get an exact non-order of magnitude difference frequency, then you would use your equation for the gain outside of your passband, which is it's ZF over ZI. You actually include the capacitor. Yeah.
Is at the passband and at the cutoff frequency the same thing?
The passband will be this whole region. The cutoff frequency is very specific. That's where we have the -3. So if we're in our passband, we use this one.
Okay.
If we're at the cutoff, then we use this one -3. Which is, oh, sorry, yeah, this is misleading. I should say at cutoff. Sorry about that. At the cutoff frequency. Cutoff frequency is very specific. In the passband, we use a passband frequency. At the cutoff, we subtract 3 decibels, and past that, we have to use our attenuation equation or this minus 20 decibels per decade. Okay, make sure you don't add 20 decibels if you're moving away from your passband. If you're moving away from your passband, you're always decreasing the gain, so the decibels have to decrease. You have to subtract your decibels. But with that, that puts us a little bit over time. I hope that we got through a lot of good information. There's some more examples that we could have done, but if you understand what we talked about today, I think you're going to be fine for the exam. Yeah, any other questions? Yeah. Yeah. That's for this linear approximation of the gain here. It's a slope of about 20 decibels per decade, or every time you multiply by a factor of 10. So we subtract that from our passband gain, because that approximation matches with our passband. So anytime you're going to do the minus 20 decibels per decade, you have to do from your passband gain. Yeah. So that's why we use the 29.12 minus 20. Get the 9.12. Oh yeah, don't forget to take a selfie if you need to. Wait, hold on. I'm gonna ask. All right. Anyone online have any questions?
I don't know.
You said that was fine.
Okay, I'm gonna go ahead and end the recording. Thanks for coming. I hope that it was useful, and this will be posted to the IEEE Discord. Go ahead and message anyone in the Discord if you have any further questions before the exam.